Hi guys, it's been a long while, but I'm back with another video. Today we talk about vector embeddings and specifically about using them with Postgres DB, the everything database. So let's start. What do we have? What we do? So we'll have Postgres database with pgvector extension that will allow us to use vector embeddings type. Postgres will integrate with OpenAI and Google APIs to generate real embeddings, and we'll show how you can implement semantic search using this based on the data from Kaggle data notebooks, which we'll cover in a while, and to test the limits of performance for those embeddings. In Postgres, we'll also have performance test embeddings. These will be artificial ones. We generate about 1 million of them to test whether it still performs good enough. Because with OpenAI and Google embeddings, we'll have around 100,000 of them, because this is how much records we have in this dataset. And Postgres will be in Docker. As often we have our app in Java 21, so we need to have that. We have a few bash scripts, and you do need to have API tokens for OpenAI and Google AI platform. Yeah, and that's it. So let's start. So before doing all of that, let's maybe reiterate what the vector embeddings are. So they're basically a numerical representation of any information from the word. So we can take text or image or a video even and turn it into a vector, which is a number of arbitrary dimensions. In this example, we have two vectors of 3 dimensions. In practice, they have hundreds of or even thousands of dimensions. And we can take two of vectors like that, calculate the distance between them. Euclidean distance we have here. There are other types, but it is not that important. What is important that by comparing distance between two vectors, we can tell how similar they are. And dimensions, for what they mean, it depends on the type of data, but for text, they represent semantic meaning of the text. So if we have two words, two sentences that have similar vectors, it means that they mean something similar. For images, they have similar visual patterns. So it is quite useful. So knowing that, we can start. We go to README. Some of the steps we'll skip, like generating OpenAI and Google vectors, because it can take a while. I have pre-generated them, but there are scripts ready to be used if you want to repeat those steps on your own. So first we need to run Postgres DB. So let's do that. I am in the Postgres directory as we have described here. So I will just run this command. It's quite fast for me because I have run it before. So if you run it for the first time, we need to download the pgvector image from the internet, so it can take a while, but outside of that, we just have init SQL script, which creates the database and user, and it creates also vector extension so that we can use vector type. Yeah, going back to README. So we have Postgres. Right now we'll start Java app. We'll build and start it. For that we need to have two API keys. If you don't need to generate those vectors and use it, you can also put dummy value there, but we will do that. So right now I will export my API keys. Right, I have exported my API keys, so let's build and run the embeddings or vector embeddings app. Alright, it is getting built. Okay, and again, it can take a while for you if you don't use Spring Boot usually, because we need to download all the dependencies. Alright, but we do have it, and we can validate that it works by going to the Swagger UI. So it works, as you can see, and as the next step, we'll download the data from Kaggle. I think it is called. So here we have it. Let's download it. Yeah, I'm downloading it. Once it is done, let's go to this folder. Actually, let's extract it here. It is extracted, so let's actually open it in the terminal. See what path do we have here. It's this. Let's see what we have here. So right now we need to load it. I have loaded before, but let's validate it. It works. So I can also let's run it without this variable, and as you can see, we need to have it. So let's export it. So it is what? It is that. Archive and books dataset. Right, now it should work. We can see logs somewhere here. We are loading the books data. Let's see. Should be quite fast. Alright, it took a few seconds. Let's see how the database is doing. Yeah, pretty low. And also we had how much? 103,000. So let's do PSQ. Let's go to the Vector Embeddings DB and validate that we do have things there. So we have a few tables, and let's count the embedding data. From right. So it was less because not all of them are unique. So we need to do then is to generate OpenAI and the Google embeddings, and I will skip that, as I said, because I have done that basically, and it can take a while, especially that you may have some rate limits. For OpenAI, almost surely you need to pay for that because the rate limits are like 3 requests per minute. For free tier, for Google, I didn't need to pay. They have quite, they give you a lot of free requests to that end, almost no rate limit as far as I know, or it is very generous. But in any case, if you run those scripts, which can take a while, you should have the same amount of data in the related tables as we have in Vector Embeddings data. So for OpenAI books, it's the same as you can see, and for Google, it should be the same as well. Alright, so we have that, and we can go, because we need to generate it, but we have it, so we can go to our UI and see some of the interesting results. I have prepared a few interesting inputs. Let's see what we'll get there. Should be faster. Let me plug a charger, I think that's the issue. Yeah, let's run it again. Yeah, charger was the issue. So as you can see, it is quite fast. A second. Right now it was 6 because of the charger, but in any case, wartime experience. As you can see, we have interesting related results. Purchase stories of the war, my war, yeah, and this was for OpenAI. Let's maybe get more results out of curiosity. Yeah, still related, but obviously less and less. Let's see what the Google's model will give us. Yeah, I changed the input, not the model. Yeah, for the model, we also have created input, but as you can see, it is different, but still related. Embeddings are created based on title and description, but as you can see, many books, they don't have description. Yeah, so let's maybe take hierarchy as well. I will save a few for your experiments. For hierarchy, you got the order of things, obviously related to hierarchy. The social order, also related. Authority, leadership, freestyle equals. Interesting. Let's take OpenAI once again, compare the results. So first, yeah, the same. Yeah, first results is the same, but we have pyramids, which is interesting. Yeah, feudalism, also related, obviously. Structured computer organization. And we have hierarchy there. Interesting. Let's maybe take outside this story with OpenAI first. Japanese culture, related, obviously. Asian art, the Western tradition. That's interesting that it judged it as related, even though, I mean, we have direction there, like east-west, but it's not about east. But yeah, interesting results. Let's take Google again. good model again. Yeah, slightly different results, as you can see, also very good, related. Yeah, interesting. As you can see, I can have pretty interesting searches, search engines based on that. Yeah, but as you can see, if we type something like that, the results are quite fast, second, even less, sometimes a little bit longer. Yeah, but these are singular requests. It's not loaded at all. We just type something, and we don't have indexes, but we only have 100,000 rows in the table. So, but it would be more loaded in the real environment. So for that, let's run the load test as we have here. So go to the load test directory, export a few variables. We'll make 50 requests with only 2 requests per second. Frequency, let's take the OpenAI model, data source books as we did on the UI, and let's run it and see what will happen. Let's maybe see what the database is doing. Yeah, lots of CPU is taken, as you can see. We have 200% because we have 2 CPUs. Yeah. But it is taking quite a while. Yeah, but not tragic. 2 seconds. Yeah. Yeah, but I got worse results here. So let's validate actually that we don't have an index there. Maybe I forgot to no, but we don't. So let's maybe try one more time with 5 requests per second. Because here, as you can see, I've got worse results. Actually, closer to 10 seconds. So let's compare it. Yeah, so right now it was similar with 5 requests per second. Yeah, but even with 5 requests per second, as you can see, it's not acceptable. Most of the requests, they took more than 7 seconds, close to 9. Close to 9 even, and yeah, here similar. Right now results are similar, but I've run the 5 requests per second, not 2. Maybe I didn't have my charger on, to be honest. Yeah, so right now what we do is we will index it, because as we reject, we don't have an index there. So let's create inverted file index with flat quantization. This is the simplest index type for the vector embeddings. It will take a while. Oh, it already has finished, I believe. Yes. So right now we have an index. You can also see its size. Let's do pg size printing, pg total edition size, and name of the index. Right, almost 1 gigabyte. Yeah, so let's run our test Here, let's run our test again. Previously we had over 8 seconds on 9%. Let's see how it will perform with the index. Alright, so you can see significantly better, so less than 1 second actually for the 9th percentile. Let's actually run it again and see the database. CPU is low, as you can see, and previously it was over 100%, even close to 200. So yeah, performs really well. But what about more data? So for that we have performance test vector embeddings, and let's maybe go to the code right now. We hadn't previously. So for the Google, we just have integration with its API. So we have HTTP. We use a standard Java HTTP client to make HTTP requests. We have simple input data as the input, string data, some arbitrary ID. The ID is basically, where we have it, it's basically this. For books, it is some arbitrary hash. So we have that, and yeah, this is input for the embeddings that we have seen on the UI, and this ID is just some arbitrary hash created based on this data. Yeah. And for OpenAI, we have something similar. We also integrate through the API, making HTTP requests, taking model, which is not important here, and input and text input to generate vector, which is just list of float numbers. And for performance vectors, we have the same number of dimensions as we have for OpenAI, which is higher, over 1000, as you can see. And we basically take input data and generate numbers in the range of 0 to 1 for each dimension. Yes. So to generate those, if we go back to README, I have also a script, and it can take a while because we have 1 million embeddings. So I have done it previously. So if we run count on the performance test table, we have 1 million vector embeddings. Let's validate again that I have removed indexes from it. Yeah, we don't have it. We don't have indexes. So for you need to run this script. It will, in a few minutes, 21 for me, generate you and save 1 million vector embeddings in your database. Then, once we have it, let's run the load test. Our load test again. So less requests, as you can see, and performance test model and data source. Let's run it and see whether it can handle our load or not. Yeah, I think we have timeouts already. Probably database, yeah, it's using its maximum capacity, close to 200% CPU. So yeah, we have lots of timeouts, and I think it was similar for the results that I have run here. Yeah, it probably will be close to 10 seconds again, and almost all of the requests they will timed out. So let's see, 200% probably will be similar. Yeah, basically the same. All timeouts. We have a timeout of 10 seconds, so not acceptable at all. And as you can see, we didn't cancel all of the queries, so they're running still. So that's why before indexing the database, let's restart it. Yes, and let's reindex, and this will take a while because the table is larger. It has 1 million records, and interestingly, we can see its progress. So CPU is loaded, as you can see. Yeah, it is work in progress, so we need to wait a few minutes. And in general, for this index to be performant, you need to generate it after you have most of your data, or preferably all of your data. And if it changes a lot, you should reindex it. So you should run it at some frequency if your data is changing. That's the drawback, but it is true for all type of indexes for the vector embeddings, unfortunately. And the index that we are using right now, which is the simplest index, inverted flat file index with inverted file index, I think, with flat quantization. It basically creates a few centroids using Cummins algorithm, and in those centroids you have clusters of vectors. So in our example of generating for this table, we have 1 million embeddings. We'll create 1000 clusters using this K-means algorithm, and at each cluster, each of this 1000 clusters will have vectors that are closest to this cluster, and it has more or less linear complexity, because then we only check one or a few closest to given vector clusters, closest to the vector that we generate based on the user query, basically. Yeah, so as you can see, it will take a while, 24%. CPU is loaded, and also we have 2 CPUs and 8 GB of memory. So if you generate it regularly, probably need to, at least for the duration of generation, need to have some more resources, or your database needs to be not used that much, because as you can see, it's really loaded. And for the other index that I don't go over here, but I have also prepared scripts for it, which is hierarchical navigable small words index. It takes even more resources and time to generate it, and its performance is a little better, but it is more complicated. And as we saw and we'll see, performance of this index is good enough. Alright, but let's see. Yeah, let's wait. Then we'll see how it performs, basically. Right, guys, we have it. It took 7 minutes. Yeah, even closer to 7. Yeah, 7 almost 7. Alright, but in any case, we have it. Let's check our table that it exists, just out of curiosity. Yeah, we have it with 1000 lists. As I said, lists are clusters. Yeah, and we have linear complexity. We need to check all lists, 1000 in our case, and in n lists that we configure, I configure to check 3 first lists. We brute force in every inside every list. And we have 1 million rows, so in every list there is approximately 1000 vector embeddings. Yeah, but that's theory, and let's run our test again. So yeah, let's go to load test. Yes, let's set environment variables again, and it didn't make this, as you can recall. As you can recall, we didn't make this previous time, so let's run it again. Actually, I think I have this set up. Yes, so 25 requests, and as you can see, we don't have timeouts, so, and CPU is low. Yeah, and we have amazing times, as you can see, 100 milliseconds. We have 1 million records, vector embeddings in the table. So let's do the more serious tests. More serious tests as we have here. So 1000 requests and requests per second 50. And let's see. Let's check the CPU. Yeah, higher, but still quite low. Remember that we have 200%, so it is less than a half. We have 2 CPUs. Let's see the times. Yeah, amazing times. As you can see, 99th percentile, less than 40 milliseconds. Yeah. So do we need more, guys? As you can see, the Postgres can handle all the cases that we need with vector embeddings. 1 million rows, probably it would handle similarly well a few million, 10 million, maybe even 100. And then you can partition your tables, shard your database, and so on. So simple Postgres with pgvector extension. And with the simplest index, which is inverted file with flat quantization index is good enough to handle your vector embeddings use cases. So I think that's it, guys. If you like the video, subscribe to the channel, and I see you in the next one. Cheers!